We spent a lot of time talking about the sophisticated software running the modern world.
Right, the AI, the cloud architecture.
Yeah, exactly, the data pipelines and all of that. But we rarely stop to look at the hardware that actually keeps the physical plant from blowing up while that software is running. I'm talking about the invisible danger that's just inherent in industrial spaces.
It is so easy to forget that. I mean,
Yeah.
if you're standing in a refinery or a wastewater treatment plant or a semiconductor fab, the atmosphere itself is often the primary threat.
Yeah.
You have these colorless, odorless gases that can be toxic in parts per billion,
Yeah.
or combustible vapors that are just, waiting for a single spark.
Right, exactly. And that is why today we are doing a deep dive into a piece of hardware that acts as the sentinel for those exact threats. We are looking at the Teledyne Detcon Model 700.
Which is quite the piece of equipment.
It really is. Now, the documentation we are pulling from the technical brochure and their spec sheets today, it calls it an industrial gas detection sensor, which is accurate, I guess, but it feels a bit undersold.
Just a little bit, yeah.
Because after parsing through the specifications, this thing reads less like a standard sensor and more like a survival capsule for electronics.
That is a very fair assessment. When you look at the Model 700, you are really looking at an exercise in engineering resilience.
Yeah.
This device is designed for what are technically classified as harsh and extreme locations. We aren't talking about a climate-controlled server room here.
No, definitely not.
We are talking about offshore platforms with constant salt spray, deserts with baking heat, and processing floors where literally everything around it is vibrating constantly.
So the mission for this deep dive is to unpack how you engineer a device to not only survive those brutal conditions, but to remain accurate enough to save lives. We have the technical specs, the material breakdowns, the performance data. We need to figure out how this bulletproof design actually works.
And, maybe more importantly, why the industry relies on this level of hardening. And it is worth noting right at the start, environmentally bulletproof is the actual claim they lead with in the brochure. In the world of instrumentation, that is a highly loaded phrase. Usually when marketing says that, it just means water resistant.
Like it can take a splash.
Exactly. But here, the implementation is quite specific and extremely physical.
Well, let's start with the skin of this thing then. The housing. It is made of electropolished 316 stainless steel. Now, for our listeners who work in heavy industry, 316 stainless is standard issue.
Yeah, it's a baseline for corrosion resistance.
Right. But I want to zero in on the electropolished part, because my first thought was, is that just for aesthetics, making it look premium out of the box?
It definitely does look premium, but in a chemical plant, absolutely nobody cares about aesthetics.
Fair point.
Electropolishing is a critical functional choice. When you machine stainless steel, you leave behind microscopic peaks and valleys. Surface roughness?
Even if it feels smooth to the touch.
Exactly. And those microscopic valleys are where contaminants hide. So in a marine environment, salt gets trapped in there. In a chemical plant, acidic vapors condense and pool in those microscopic ridges.
And that leads to pitting corrosion, right? Because even stainless steel will rust if you give the acid a place to sit.
Precisely. Pitting and crevice corrosion. So what electropolishing does is it dissolves those peaks on a microscopic level. It physically reduces the surface area and creates a passivated layer that is incredibly smooth.
So it's like leveling the playing field.
Yes, which means water just beads right off, contaminants can't stick, and corrosion has a much, much harder time finding a foothold. It is all about longevity in environments that eat lesser metals for breakfast.
Okay, so the shell is hardened. But let's talk about the internals, because the biggest killer of electronics in these environments isn't always the corrosion. It's vibration and moisture ingress. The specs mention the electronics are 100% encapsulated.
This is a slightly controversial but absolutely necessary design choice for this class of device. Encapsulation, or potting, as it's called in the field, means the entire circuit board is submerged in a liquid compound that then hardens into a solid block.
The trade-off there, obviously, is repairability. I mean, if a 10-cent capacitor blows on the board, you can't just go in with a soldering iron and swap it out.
No, you're swapping the whole module.
Which sounds expensive.
It is, but you have to weigh that against the failure mode. If you're in a facility with massive compressors and pumps running 24/7, you have constant low-frequency vibration.
Right.
If you have a standard printed circuit board with air gaps, those components vibrate. Solder joints crack. Connectors experience what's called micro-fretting. where the tiny metal contacts rub against each other until the connection just fails.
And a loose connection in a gas detector isn't just an annoyance, it's a massive safety hazard.
Exactly.
Yeah.
By encapsulating it, you turn the delicate electronics into a solid brick. The components cannot move relative to each other. Period.
And I imagine it helps with the water, too.
Oh, it completely eliminates the risk of water touching the board. You could blast this thing with a high-pressure hose during a facility washdown, or have severe condensation cycling every single night, and the copper traces will never see a single drop of moisture.
So you sacrifice that component-level repairability, which, let's be honest, practically nobody does in the field anymore anyway, for near-total immunity to vibration in water. That makes total sense.
It's the only way to guarantee it survives.
But what about the electrical environment? Because these plants are really noisy places, electrically speaking.
They are absolute nightmares for sensitive electronics. You have variable frequency drives, VFDs, starting up huge motors all the time. You have welding equipment operating nearby, handheld radios everywhere.
And the Model 700 specs specifically list bulletproof I/O protection. There's that word again, bulletproof. They really lean into it.
They do, and in this context, the bulletproof I/O refers to EMI and RFI immunity. That's electromagnetic and radio frequency interference.
So stopping the noise from messing with the signal.
Right, because without robust filtering, a technician keying a walkie-talkie 5 feet away could induce a current in the wires that the sensor interprets as a massive gas spike.
Oh, wow. So the radio causes a fake gas leak.
Exactly. That leads to false alarms. And in this industry, false alarms are incredibly dangerous because they breed complacency. If the alarm goes off every time someone uses a radio, people stop evacuating.
Or they just shut down the whole production line, which costs the company millions. The brochure also mentions overvoltage and miswiring protection, which is just recognizing the reality of field installation, right? Sometimes wires get crossed.
It absolutely happens. You don't want a simple wiring error during the initial commissioning to instantly fry a piece of life-saving safety equipment. It's about making the device robust against human error just as much as environmental stress.
And they built it to be modular, too. There's a junction box, a surge protection termination module, and a splash guard. It really just sounds like a tank designed to sniff out gas.
That's a great way to put it.
Let's pivot to the brains of the operation, then. Having a tough shell is great, but if the sensor inside drifts or just fails silently, it's basically an expensive paperweight. The documentation heavily emphasizes its ILL rating. Specifically SIL, too.
Right, and this is where we get into the actual math of safety. SIL stands for Safety Integrity Level. It comes from the IEC 61511 and IEC 61508 standards.
So it's an international benchmark.
Exactly. It's not just a marketing badge you buy. It's a rigorous statistical calculation of probability.
It's about the safe failure fraction, according to the text. But for the actual operator sitting in the control room, what does SIL2 really mean in practice?
It means the device is designed to proactively tell you when it's broken. That is the fundamental difference here. Let's say you have a basic non-SIL sensor. It might fail. The sensing element burns out, for example, and the output just drops to zero.
And to the control system, zero gas looks like safe air.
Exactly.
Yeah.
You think the air is clean, your system says everything is green, but actually your sentry is dead.
That is genuinely the nightmare scenario in a refinery.
It is. So a SIL2 rated device like the Model 700 has preemptive diagnostics. It constantly monitors its own input voltage range, its operating temperature range, the detector signal amplitude, and the output signal loop integrity.
It's checking its own pulse.
Constantly. And if it detects a fault in any of those parameters, it doesn't just sit there reading zero. It deliberately drives its output to a specific fault state. Usually that's a signal below the standard 4 milliamp baseline, specifically to signal to the control room, hey, I am not working.
So it differentiates between I detect no gas and I cannot detect anything.
Correct. It forces a maintenance response before a real gas leak happens.
And looking at how it actually communicates this, it uses dual redundant outputs. You have the traditional linear 420 milliamp analog signal, which is just the absolute industry workhorse, and a Modbus RS-485 serial output, and they can run simultaneously.
That redundancy is really interesting from a systems architecture standpoint. Well, you could have the highly reliable analog signal going straight to your emergency shutdown system, the simple hardwired safety loop that just trips the plant if things go wrong. And at the exact same time, the Modbus data is streaming to your asset management software to track the detailed health diagnostics over time.
So it bridges the gap between the legacy safety infrastructure And the modern industrial Internet of Things approach, where you want rich data on absolutely everything.
Exactly. It serves both masters perfectly.
All right, let's get to the business end, the nose of this thing. The Model 700 is described as a universal design, meaning the main stainless steel body is the same, but the gas detector sensor elements are plug-in components that you swap in the field depending on what you're hunting.
This modularity is a huge deal for inventory management at a large plant. You only stock one type of housing. But the real story is the breadth of technology they've crammed into these little plug-in modules. The brochure lists 6 distinct sensing technologies.
Yeah, let's break the big ones down because there are some truly impressive numbers here. First up, hydrogen sulfide, H2S. This is the big bad in the oil and gas sector.
H2S is just nasty stuff. It's deadly at incredibly low concentrations, and it's highly corrosive to equipment. Traditionally, the industry detected this with electrochemical cells.
Which are basically tiny batteries, right?
Essentially, yes. They work well, but they rely on a chemical reaction. And because of that, they get used up. If you put them in hot, dry environments like a desert facility, the electrolyte inside the cell can actually dry out.
But the Model 700 uses something different. It says ChemFET-MOS solid-state technology for H2S. And the warranty on this specific sensor is what caught my eye, a 10-year sensor warranty.
In this industry, that is massive.
Yeah, that seems unusually high.
Most electrochemical sensors are warranted for 2 years, maybe 3 if you're lucky. A 10-year warranty suggests a fundamental shift in the physics of how they are doing the detection. Solid state means exactly what it sounds like. There's no liquid electrolyte to dry out.
It's a metal oxide semiconductor.
Right. The gas interacts directly with the surface of the semiconductor and changes its electrical resistance, but it doesn't actually consume the sensor material in the process.
So from an operational expense perspective, an OpEx perspective, that's a game changer. You install it and you literally don't budget for a replacement until the mid-2030s.
Assuming the plant's electronics hold up, yes, it changes the maintenance cycle completely.
Now compare that to combustible gas detection, things like methane or propane. This is usually done with catalytic beads.
The cat bead is the old standard. It's been around forever. It's basically a tiny coil of wire coated in a specific catalyst. When combustible gas hits it, it actually burns on the bead.
Oh, it physically burns the gas.
Just a tiny amount, yes.
Right.
That heats up the wire, and we measure the change in resistance due to the heat. It's simple, and it's very reliable. But they have one major Achilles heel, and that's poisoning.
Right, if you have certain chemicals in the air, like silicone vapors or sulfur, it coats that little bead and permanently kills it.
And the really scary part is, a poisoned catalytic bead reads 0. It fails unsafe. It won't tell you it's dead until you hit it with test gas and nothing happens. That is precisely why the Model 700 offers an infrared, or IR, option for combustibles.
The text calls it a miniature plug-in optical detector. How does going optical solve the poisoning issue?
Because IR is purely optical. It shines a specific wavelength of light through the gas chamber and measures how much of that light is absorbed by the gas. There is no chemical reaction taking place. There is no burning.
So the silicone or sulfur in the air just passes right through?
Exactly. Silicone, sulfur, even a complete lack of oxygen, none of that matters to an IR sensor. It's completely immune to poisoning. And they give the IR sensor a 5-year warranty, which backs up that durability.
So if IR is that much better and immune to poisoning, why doesn't everyone just use IR for everything?
Well, cost is definitely one factor. IR sensors are more expensive. But the bigger issue is just physics. IR simply cannot detect hydrogen gas.
Wait, really? Why not?
Because the hydrogen molecule doesn't absorb infrared light at the wavelengths we use. It's invisible to the sensor. So if you were working in a hydrogen plant or a battery room where hydrogen off-gassing is the risk, you must use the catalytic bead or a specific electrochemical sensor. It's all about matching the physics to the specific hazard.
Speaking of matching physics, let's look at the nasty list. The brochure lists a huge array of detectable gases. You have the standard ones, oxygen, carbon monoxide, methane. But then you get into the exotics. I'm seeing arsine, bromine, diborane, germane.
Yeah, now we're leaving the traditional oil patch and entering this semiconductor fab.
That's a whole different world.
It is. Gases like arsine and germane are used in doping silicon wafers to make microchips. They are incredibly toxic. We are talking far, far more lethal than H2S.
So the stakes are even higher.
Much higher.
Yeah.
For those gases, we are measuring in the parts per billion range to ensure worker safety.
I noticed something interesting about the warranties when we get to these exotics. We were just praising the 10-year solid-state H2S sensor and the 5-year IR sensor. But look at fluorine. The warranty drops to 1.5 years. Ozone is 2 years. Volatile organic compounds, VOCs, are just 1 year.
This is a perfect example of how you just can't cheat chemistry.
What do you mean?
Take fluorine. Fluorine is the most reactive element on the periodic table. It desperately wants to react with literally everything it touches. So detecting it usually involves an electrochemical sensor that is, by its very nature, being chemically attacked by the gas it's trying to detect.
Oh, wow. So a 1.5-year lifespan isn't a manufacturing defect, it's just the cost of doing business with fluorine.
Exactly. The sensor is actively sacrificing itself to give you that reading. If you ever see a manufacturer claiming a 10-year life on a fluorine sensor, you should be very, very skeptical. The PI-700 specs are just being honest here. They reflect the harsh reality of the chemistry.
And then there's the VOCs, the volatile organic compounds. They use a PID, which stands for photoionization detector.
Right. Think of a PID as a broad-spectrum sniffer. It uses an ultraviolet lamp to blast the gas molecules, physically breaking them into ions so it can measure the current.
And the specs call it a universal non-selective VOC sensor.
That non-selective part is key. It's excellent for detecting a leak of something hazardous, even if the sensor can't always tell you exactly what that something is. It just says, hey, there's a bunch of organic vapor here, be careful.
Let's shift gears to the actual user experience, because this is one of the weirdest challenges in industrial design. You have this device that periodically needs to be calibrated, right? You have to tell it, this is what zero gas looks like, and here's a test bottle, this is what 50% gas looks like.
Routine calibration is mandatory, yes.
But the sensor is located in a Class 1, Division 1 hazardous area.
Right, and that designation means an explosive concentration of gas is likely to be present during normal, everyday operations.
So you can't just open the metal box to press the calibration buttons. The warning label on the front is literally in all caps. Caution open circuits before removing cover. And keep cover tight while circuits are alive. If you unscrew that lid while the power is on, the tiny spark from you pressing a button could blow up the entire facility.
Which creates an absolute logistical nightmare for maintenance teams.
I bet.
To calibrate a standard old-school sensor, you need what's called a hot work permit. You have to use a portable gas sniffer to prove the immediate area is perfectly safe. Then you might have to de-energize the safety loop, carefully open the box, make your mechanical adjustments, close it all back up, and re-energize.
That sounds exhausting.
It can easily take 2 technicians several hours just to do one sensor.
But the Model 700 claims its interface is completely non-intrusive. It uses internal magnetic programming. This is the magic wand part. Describe to me how this actually works in the field.
Okay, imagine you are the instrumentation technician. You're wearing thick rubber safety gloves, maybe a full Tyvek suit, safety glasses. You have a small, handheld magnetic wand in your pocket. You walk up to the Model 700 on the pipe. Through the glass window on the front, you see an LED display scrolling.
Okay, I'm picturing it.
You don't unscrew anything. You simply touch that magnet to the outside of the glass over specific marked spots on the casing.
So there are magnetic switches behind the glass, Hall effect sensors probably.
Exactly. They sense the magnetic field through the solid glass. You tap the magnet to enter the calibration menu. You hold it to select an option. And the alphanumeric LED display behind the anti-glare cover walks you right through it.
Oh, the specs give examples of the script. It says things like APLIY 50% ELL, and then when it's done, it says span OK, remove gas.
Right, and it even tells you sensor life 100%.
And the whole time you never crack the seal on that explosion-proof housing.
Never. The explosion-proof integrity of the unit was maintained the entire time. You didn't need a hot work permit. You didn't need to power down the safety system. A 2-man job that used to take 2 hours now takes one person about 10 minutes.
It's so interesting to me how low-tech that interface sounds, a magnet and a scrolling LED display, but it elegantly solves a very high-tech, high-stakes problem. There are no delicate touchscreens to fail, no physical buttons to get gummed up with dirt.
And that scrolling text is vital. It gives incredibly clear feedback. It removes all ambiguity. When you're standing on an elevated gantry in the freezing rain, you don't want to be deciphering complicated blink codes from a single tiny light. You want the machine to just talk to you in plain English.
Let's round out the hardware specs with power and integration, because this thing is surprisingly efficient. It runs on 11.5 to 28 volts DC and consumes less than 2 watts of power.
That ultra-low power consumption is actually very significant for facility design.
Because of the scale.
Yes. If you have a massive processing plant with 500 of these detectors deployed, the difference between a sensor drawing 2 watts versus 5 watts is a massive difference in your central power supply requirements, especially when you have to size your backup battery arrays to keep the safety systems running during a total power outage.
That makes a lot of sense. And looking at the certification list, this thing has a passport thicker than mine. It's got approvals everywhere.
Right.
CSA, ATEX for Europe, in Metro for Brazil, CNEX in China, PISO in India, and ABS.
I'm glad you brought up ABS. That's the American Bureau of Shipping.
So that's the marine certification.
Exactly. That means it's fully rated for use on ships and offshore drilling rigs. That brings us right back to the vibration and corrosion resistance we started the conversation with.
Full circle.
The environmental standards for marine electronics are notoriously brutal. Getting that ABS stamp means this design really has survived the ultimate torture tests.
They also mentioned a few accessories that caught my eye. The ability to add a wireless interface module or a heart RAM module right in the junction box.
That's all about retrofitting. Let's say you manage a 30-year-old plant and you just can't afford to run miles of brand new copper conduit to install new sensors. You could slap a wireless module on the Model 700 and integrate it that way.
And the heart module.
If you have a legacy control system, you use the HART protocol to superimpose digital diagnostic data right over the old analog copper wires. It allows this brand new, smart tech to live comfortably inside the old infrastructure.
So bringing this all together, the Model 700 really represents a convergence, doesn't it? It's the brute force physical toughness of the electropolished 316 stainless steel and the potting, combined with this highly sophisticated digital intelligence of the SIL2 diagnostics.
It absolutely represents a shift in industry philosophy.
Yeah.
The old way of thinking was basically run it until it fails and hope you catch it.
Right.
The new way, which is really demanded by the SIL2 standard, is prove to me constantly that you are working. It's a much higher standard of accountability for the hardware itself. It allows humans to monitor the unmonitorable safely.
But here is the provocative thought I want to leave our listeners with today. We are engineering these devices to be incredibly autonomous now. We've got 10-year warranties on solid-state sensors. We have preemptive self-diagnostics. We have these set-and-forget magnetic interfaces.
They are very independent.
Right. But as our industrial processes involve more and more complex and dangerous chemicals, like we talked about with the germane or the diborane, are we at risk of placing too much faith in the bulletproof box?
That is the ultimate paradox of automation reliability. The better the safety equipment gets, the less the human operators feel the need to physically check it.
Exactly. If a sensor hasn't thrown a fault in 8 years, do you eventually stop walking the line? Do technicians stop wearing their personal clip-on gas detectors because they assume the plant's sensors will catch everything?
It's a real psychological danger. Does the 10-year warranty become a license to just be complacent?
It shouldn't, but human nature is what it is.
The technology always has to be viewed as a layer of protection, not a total replacement for a strong safety culture. The Model 700 is amazing because it allows the human operator to focus on the overall process and the macro risks, rather than stressing over whether a specific sensor is waterlogged or corroded.
But the moment we assume the little metal box can never fail, we've just introduced a massive new risk into the system. It's the Swiss cheese model of safety, right? The sensor is just one slice, a very expensive, very well-engineered slice of cheese, but still just one slice.
Precisely. You always need multiple layers.
Well, next time you, the listener, drive past a refinery at night or you see those pictures of the maze-like piping in a chemical plant, look closer for those little silver cylinders mounted on the pipes because they are doing a lot more than just sniffing the air.
They are quite literally the only reason the air in those facilities remains breathable.
Thanks for joining us on this deep dive. We'll catch you in the next one.